All right. Homework assignments coming up. Active 19 is covering the stuff we're going to do today. And then hopefully we'll get to the Hess's Law stuff today as well. That is on 20, and we will talk more about Hess's Law on Friday. So those two assignments are due on Sunday. We are also going to be jumping into chapter 6. So you got several things coming up that are due Sunday, the vocabulary and the prepare to learn for chapter 6 as well. And then if you hadn't seen it on Canvas, the prepare to learn 5B over the second part of this chapter, the last section of this chapter, that's due tomorrow. So got some short assignments, some longer assignments, that kind of thing. Questions? Okay, so we are going to be talking about enthalpies of reaction. Some of the stuff in here is a little bit of review, so I'm going to zoom through it. You're not going to have time to copy it down, but you should already have basically that stuff in your notebook. But when we talk about enthalpies of reaction, what we're talking about is measuring for a mole of the reactants, making however much of the products, how much are we going to get energy-wise out of that reaction. And we can measure those in a couple of different ways, and we're going to look at those different ways here. I sometimes forget to mention this, so I want to talk a little bit about state functions. I think I mentioned this before, but let's emphasize it again. So state functions differ from non-state functions in that a state function is just the difference between 2 points. So like the difference between 2 points on a map is a distance, but the path that you take to get there, you might take a more direct route, or you might visit different cities along the way, depending on whether you go on the freeway or you take the side roads. The distance that you travel can be different. So state functions are the ones that are just what's the final position, what's the initial position. So when we talk about a state, we're talking about all of its conditions. Sometimes we talk about the phase as part of that, but we also might talk about the pressure. We might talk about the volume. We might talk about what chemicals are present in a particular system. Okay, so we talk about the final conditions, what chemicals, what pressure, what all of that, and then the initial conditions of that. So state functions only depend on those, and the way we illustrate that is with a capital letter. And these are the ones that are going to have that triangle at the front, because that triangle means final minus initial. Okay. So I could have a change in temperature that happens within a few seconds, or I could have a change in temperature that takes all day. But the difference between the highest point and the lowest point is the same, no matter how much time it takes. So we can use a triangle or delta to indicate that difference. And then it will always have a capital letter. Now notice that when we have worked with calorimetry, Q is a lowercase letter. Q and W for work, which we didn't talk too much about work. Those are non-state functions. Those are going to depend on the path. I gave you the example of the map. If we are taking a path that goes in a windy road, that's a much longer distance. All right, so there are 2 ways that I might use the energy produced from burning octane. Octane is what is in gasoline. So if I have octane and a bunch of oxygen, I'm going to end up with the final products. Now, I could just have a barrel of it and light it on fire, in which case all of that energy is being turned into heat. Or I could have it burning in an engine a little at a time, and that engine has expanding gases, and those expanding gases get moving the pistons around, and the pistons move the car forward. So then some of that energy is turned into heat, and some of it is turned into work. And so these 2 are the state functions, but the total amount of energy is the same either way. So that's the difference between a state and a non-state function. So based on what I've just said, use your fingers to tell me A for 1 and 4 for D. Which of the following is not a state function? All right, yeah, 4, because it's not a capital letter. Capital letter, it's a state function. Non-capital letter, it is not. Plus I already told you that Q is not a state function. Okay, we've talked about endothermic and exothermic and indicating things. So which sign do we use if the product is warmer than the reactants? Okay, so just think about, did that system have to produce heat, or did that system have to absorb heat? Okay, so when we say warmer, think about you as the surroundings feeling that warmth. All right, so Q being positive would be A, Q being negative would be B, and Q being equal to 0 would be C. So if I'm feeling some warmth come off of this reaction, what's the sign? A. So got some disagreement there. All right, so if I'm the surroundings, is heat entering me or leaving me? It's entering me. So it is endo for me. The system is then exothermic. So it is going from high energy to lower energy by releasing that heat. So its Q is going to be negative. Okay, so B would be correct in this. Okay, so if you look at my old quizzes, there are a lot of times that I will ask you 3 or 4 things that I'll say, is this endothermic or exothermic? Go through a series of things. And I tell you, that is a place where people can lose a lot of points. Okay, so I'll try and every day use some examples of this. And I'll try to be more specific as well. So remember, in an exothermic reaction, heat leaves or exits the system. Okay, and you as the surroundings are going to feel that. In an endothermic reaction, heat enters the system. And if you're part of the surroundings, that heat might be coming from you, so it feels cooler to you because the heat is leaving your body. All right, so let's see, endo and exothermic refer to energy change with no pressure. So when we have no pressure change, that is our enthalpy. That part's not super important. All right, so exothermic Q is negative, and also delta H is negative. Endothermic Q is positive, and also delta H is positive. So the signs that we used for Q are also the signs that we use for delta H. Okay, so remember, delta H is just Q divided by number of moles, and moles is positive, so it wouldn't change. All right, skip over that. We talked about that. Okay, stoichiometry, our favorite word. This just means that when I change the amount of a chemical, I can change the amount of heat. So when I look up on a table how much energy is produced by a reaction, it means for the reaction as it is written. So if I have 2 moles of this, and I produce 2 moles of hydrogen and 1 mole of oxygen, this is the amount of heat that I will get out. But if I change the numbers, let's say instead of 2 moles of water, I have 1 liter of water, and I have to calculate how many moles are in that liter of water. That's going to change the amount of energy. So that 573 refers to the reaction as it is written. It refers to the forward reaction, splitting the water. So if I were to do it in reverse, if I were to have a hydrogen balloon and light it on fire and produce water, then the reaction would go in the other direction and I would produce heat instead of absorbing heat. And it is quantitative. Like I said, it means for 2 moles. So sometimes on a quiz or a test, I might give you a question where I give you a reaction like this, and I might say, okay, let's say we have 100 grams of water. What is the amount of energy required to do this reaction? So you would have to go from 100 grams to how many moles there were, and then do the stoichiometry to figure out what the energy is.
So how do we get the energy?
How do you get the energy? So the energy is this amount of energy for 2 moles of water. And I'm about to do an example.
Okay.
Okay. So let's say I said, what's the amount of energy for decomposing just 1 mole of water? I'm cutting that reaction in half, right? So all of the coefficients get cut in half and the energy gets cut in half. Make sense? Okay. think I have another example in here. Yes, okay. So if you want to find the energy produced for a specific amount of reactant, so I tell you in grams, and you do need to know the enthalpy, which is that H, the delta H, for 1 mole of the reaction. So let's say your question is, what energy is produced when 10 grams of carbon monoxide react according to the reaction below? All right, so in this case, the coefficient for carbon monoxide is 1. So we don't have to do anything funny with the coefficient, but we do need to change our grams into moles. So what you're going to do is have 10 grams divided by 28. So 28 is 12 for the carbon, 16 for the oxygen. So I rounded to 1 digit here since I only had 1 mole anyway. And I'm going to, I'm sorry, I have 3 digits on the 10 grams. That's why I did. So that's going to give me 0.357 moles of carbon monoxide. So I could set up a proportion. Some people like to do it as proportion. Or I could say, okay, let me just multiply the moles times kilojoules per mole, because mole is in the bottom. Okay, so that'll cancel my moles. So think of this as a percent, like what percent of this energy is going to be produced. So I'm taking this, multiplying it by this, and that's how I get that energy. Okay. And I'll do another example of that on Friday. All right. So today what I want to talk about is enthalpies of formation. So we have lots and lots of tables everywhere for this. In your textbook, this is, I believe, Appendix G. So if you have the hard copy, you can look at it in the appendix there, or online, you'll have to go to the table of contents and scroll down and you'll see the appendix. And so what does it mean? Delta HF for sodium chloride. That means we are writing the equation where that chemical is the only product and the reactants are its elements. So the elements that compose sodium chloride are sodium and chlorine forming sodium chloride. So we have some rules about how we write the elements. They have to be in their most stable form and neutral. So we're not having the charges of them. So sodium isn't particularly stable, but the only stable way to have it as a pure element is as a solid. Okay. Chlorine, the only stable way to find it is diatomic. That's one of the reasons why we want to know which are our diatomic elements. And I keep referring you back to the dark green over here. All right, so we want to balance the equation. This is the one occasion where we're allowed fractions. Normally we don't put in fractions, but we want to make sure we only have 1 mole of the product, because this is going to be energy per mole. So when I balance it all out, if this number is anything other than a 1, I divide everything by that number. So if I were to write this out normally, I would have 2 sodium, 1 chlorine gas, make 2 sodium chlorides. But since I want only 1 sodium chloride, I divide all the coefficients by 2. And then I look that up in a table. This isn't something you can figure out from the periodic table or do a little math and understand. It has to be done experimentally, so that's why we have tables. When I look it up in a table, I'm going to see this number. Okay, and that is the equation that is implied by this number. Okay, so I'm going to switch over now to this piece of paper that I did. So, tables of standard enthalpies of formation. So remember, enthalpy is H. And then we put a little F there to be formation. Standard, we show with a little circle. So you will see that little circle there. Usually, even if we don't put the circle, we're going to assume it's standard conditions unless you're told of it. So this gives the energy required to do what? What were we doing with the sodium chloride in that example? We're making it, right? We're forming it to produce, make, form, whatever word you choose. And how many moles? Just one. Okay, so as a definition, you need to know this. And then as far as the standard state is concerned, it's similar to, but slightly different than for gases. So for gases, we said 0 degrees Celsius. For thermodynamics, it's 25 degrees Celsius. So it's kind of a round number, but it's also a lot closer to room temperature. As I mentioned from time to time, that is a little bit warmer than we typically like our room temperature, but it's not unreasonable. Okay. We're still at 1 atmosphere. Now, sometimes we have chemicals that are in solution. So if it is an aqueous solution, we assume that it is 1 molar solution. And then if we have a solid or a liquid, this is for a pure solid or a liquid. All right. So this paper is going to be one of those things that I would collect as an extra credit opportunity at the time of your next test, right after Thanksgiving. So we're not going to do the rest of it, but what you would do is there are a couple of things down at the bottom here. These get cut out. I'm going to zoom out a little bit here. All right. So these cover up this. So you can use that as kind of a test yourself. What do the reactants have to be? What do the products have to be? Well, the reactants have to be elements in their standard states. The products have to be 1 mole. Then you need to do, let's say, 4 of these examples. All right, we already did sodium chloride, so that can't be one of your examples. So do 4 of the others to determine what they are. Okay, so if I were going to do, let's do one that's not on here. I'll do it, well, I'll do that in just a second. And then these 2 things get cut out and cover up what are monoatomic elements and what are diatomic elements. So what does this Brinkelhoff mean?
Oh, this diatomic.
Yeah, each of those are the element symbols shoved together to be the diatomics. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Just so you know what those things mean. Okay, so let me do an example of it's out of here. It's a good chemical. Let's say I wanted to do glucose. So glucose is C6H12O6. So if I had on a quiz or test, write the equation for the formation of glucose, that's going to give you the enthalpy of formation. This would be our product. Okay, and that's a liquid at room temperature. I would tell you that. So I have to have each of these elements. They can't be in compounds, and they have to be in their most stable form. So I'm going to have carbon is a solid. I'm going to have hydrogen. And then I have to think to myself, is hydrogen going to be diatomic? Mm-hmm. That's the H in Brinkelhoff. That's our dark green guy over here. And we're going to have our oxygen. Is that diatomic? Yeah. I'll put that over there. So I'm going to put the elements in their most stable form. And then I'm going to balance it. So I'm going to have 6 of these. Let's see, hydrogen, I need a total of 6. This will be 3. Hydrogen, I need a total of 12. So this will be 6. Okay. Then I'm going to check what's the coefficient over here. Is it still 1? Yeah. Yep, then I'm good to go. Okay. So you're going to do the same thing with 4 of these. examples if you want the extra credit.
Oh. But it's just balancing.
Balancing and picking the elements to put up front. Now, things you need to be careful of is you will see that oxygen can be O3. That's ozone, but O2 is the most stable form, right? So make sure you are picking the most stable form. Don't give me H. That's not the most stable form of hydrogen. I want H2 because it's diatomic. So that's what makes it tricky. Yes, you should have the states for each of them as well. So the question was, when you write it out, do you put the gas for hydrogen, the gas for oxygen? Did I leave that off on the example? Okay, yes, you should put those. Oh, to find the energy? Yes, if I asked you for the energy, you would look for that. But normally I just ask, what's the equation? What do we mean by this? Okay, so we've done an example of this. What would you do? Oh, so this is the equation that goes for ammonia. So the question might be, write the equation for the formation of ammonia from its elements. This would be the start of the answer. What's wrong with it the way that it's written? Which is what you were going to say. So yeah, sometimes people shout out, sometimes people raise their hands. But yes, it's not for 1 mole of substance. So if I ended up at this place, then what do I need to do? Divide everything by 2. And so this is how we end up with fractions. All right. So now let's look at these tables. So the second sheet that I gave you has this table on the side because it's really tiny here, and I know you can't see that from far away, but we're going to do a couple of examples. If I have a reaction where it's not from the elements, it's, like normal chemical reactions, some of them are compounds, some of them are elements, then what I can do is look at the table and figure out what's the energy of each of these compounds or elements and combine them in order to determine what the energy of the reaction is. So what I would do is, just like we do with temperature, final minus initial, we're going to do the energies, final minus initial. So we'll look at the energies of the products, because that's our final case, minus the energies of the reactants. Now, in this case, all the coefficients are 1. If they are not all 1, we do need to multiply by whatever the coefficients are. But let's do the simple example first. So we're going to do products minus reactants. So that means I'm going to look up on the table delta H of formation for each of those chemicals. So I'm going to find calcium oxide, carbon dioxide, and calcium carbonate on the tables. Generally, just like it's listed here, and this is just one line, there are pages of pages of this, it will be listed according to the element, but when you have a compound, you have multiple elements. So sometimes you might have a compound that maybe has both carbon and oxygen. So you just let me look up carbon first. If I don't see it there, let me look where the oxygen is. Sometimes you just have it in one place. All right, so if I find each of those numbers on the table, I have negative 635.1 and I have negative 393.5. Now, this is where things can get a little bit sticky because we've got these negative numbers and we are subtracting. So I have parentheses around all of the products and parentheses around the reactants to help us keep track of these things. Oops. Sorry, I forgot to advance that. So when we add up everything inside of this parentheses, we're going to have about 1,000, a little over 1,000. Is it going to be positive 1,000 or negative 1,000? Negative, because both of those are negative. Okay. And then over here, I have minus negative. So when I subtract a negative, that's the same thing as doing what? Just adding. Okay. So be careful as you're entering this in your calculator. I was doing this in another class the other day and I messed it up 3 times in 3 different ways. So you really want to check your math when you do this. And you really want to show your work, because if you show me this line and then screw up how you put it in your calculator, I'll probably only take off a point or two. Okay. If I know that you know how to set it up and it's just a matter of, oh man, I forgot to hit that negative sign, I forgive you because I make that mistake. Okay. So when I add that all up, I should end up with 178. Okay, so this first part, the products, was about 1,000 negative. The second part, we're adding on the 12,000 or 1,200. And so the difference between them is right about 200. Okay, are we ready for another example? Oh, is this going to be an endothermic or an exothermic reaction based on the sign? Endothermic is positive, so this one's endothermic. And in fact, you can get this to happen just by heating up. This is limestone. So if you take limestone and you heat it up, this is what you get. All right. I don't remember why I have this picture here, so we're going to skip over it. All right. So here's another example. And I've given you possible solutions. So take a second to look at the table and see what this might be. Oh, you know, one of A or D was supposed to be positive because those are identical, aren't they? Let's call D positive. All the sulfur compounds are down here at the bottom. All right, by show of fingers, what do you get? Two people who've given me an answer. They have opposite signs. It's products minus reactants. All right, so our product is this negative 396. And I'm just going to round it to 396 here. Our reactant is negative 296, right? So they're almost the same. They're about 100 different. Okay, so that's going to be either B or C. But since we take the product minus the reactant, the negative of the product is outweighed by adding or subtracting the negative, adding the positive of this. So this will end up being B, negative 99. All right, so even the most intelligent of us can second guess ourselves when it comes to that. So, all right. So that's basically how to do that. I'm going to switch gears now